In exercise 2.3, we need to, unless or otherwise specified, assume that all matrices in the exercise are n by n. Determine which of the matrices in exercise are invertible. Use as few calculations as possible. Justify your answer. So we need to use Theorem 8 to know that if one of the statements in Theorem 8 is true, that means our matrices from 1 to 7 is invertible. So let us check the first one. We have 2 by 2 matrix. This matrix, it is invertible if the determinant is not equal to 0, or we can check it either by the columns. If they are linearly independent, then that means A is invertible. It is clear from here we have 5 minus 3, 7 minus 6. These columns are linearly independent, so that means this matrix is invertible, because according to Theorem 8, it said if the columns are linearly independent, then A, it should be invertible, which is part E and part A. So for 1, the columns are linearly independent, because none of them is multiple of the other, so that means they are linearly independent. So from here we can conclude by the invertible matrix theorem by E, then we have A, which is A is invertible. A is invertible. Or either you can find the determinant, or this is another way. The determinant is equal. Determinant of A is 5 multiplied by minus 6 minus 3 multiplied by 7. This will give us minus 30 plus 21, which is equal minus 9. So the determinant is not equal to 0. That means our matrix is invertible. So this is the answer for number 1. Now let us see number 3. For number 3, we have a 3 by 3 matrix. We cannot say directly from here are the column linearly dependent or linearly independent unless we do some row operation. So let us do some row operation to know if this matrix has a pivot in each row. That means the column is linearly independent. That means the A is invertible. So from here we can say we may do the row operation. We may put this one to be 0, this one also to be 0. So row 2 is equal 3 over 5 row 1 plus row 2, and we may do another row operation. Row 3 is equal minus 8 over 5 row 1 plus row 3. So this will give us the new matrix here, 5 0 0, then 3 over 5 row 1 plus row 2. This will give us here 0 minus 7 0, then here minus 8 over 5 row 1 plus row 3. This will give us 0 5 minus 1. So now we have a pivot in the first one. We have in the first row. In the second row, let us make this one to be 0. So row 3 is equal 5 over 7 row 2 plus row 3. This will give us 5 0 0, then 0 minus 7 0. Then the third row is 5 over 7 row 2 plus row 3. This will give us 0 0 minus 1. So from here up to here we see this matrix is reduced to echelon form, and we reduce it in echelon form, and we have pivot in each row. That means the columns are linearly independent. And so by C also it is 3 by 3, and we have a 3 pivots. So by C then A. This is using the invertible matrix. So since A is 3 by 3 and A has 3 pivot, then we said by this one C, then A. A should be invertible, which is, it says the columns of, it says, sorry, if A has n pivot positions, then also A is invertible. So this is for 3. Now let us see 5. Also we have a 3 by 3 matrix. We need to do some row operations. So we need to make this one in echelon form if we can. And let us see if this one has also 3 pivot position or it has less than 3. So we may interchange between row 1 and row 2. So row 1 and row 2, we interchange between these two rows and we get 1, 0, 2, then 0, 3, minus 5, then minus 4, minus 9, 7. Then let us make this one to be 0. So row 3 is equal for row 1 plus row 3. This will give us 1, 0, 2, 0, 3, minus 5, then 0, minus 9, 15. Then we have a pivot in the first row. Then let us see, here we have also a pivot. So let us make minus 9 to be 0. So row 3 will be equal to 3 row 2 plus row 3. This will give us 1, 0, 2, 0, 3, minus 5, and here we have 0, 0, 0. So now this matrix is a 3 by 3 and we have just only 2 pivot. So A does not has an pivot position, that means A is not invertible. So since A is a 3 by 3 matrix and A has only 2 pivots, we cannot reduce it to I3, hence A is not invertible. So A is not invertible. لأنه theorem it said if one of the statement is false, all the others will be false. So since A is a 3 by 3, so we should have 3 pivot positions for A to be invertible. But here we have only 2 pivots, so that means A is not invertible. Now for 7 we have a 4 by 4 matrix. Let us do some row operation to see if A is invertible or not. In exercise 11 and 12, the matrices are all n by n. Each part of the exercise is an implication of the form if statement I, then statement 2. Mark an implication as a true if the truth of statement 2 always follows whenever statement 1 happens to be true. An implication is false if there is an instance in which statement 2 is false but statement 1 is true. Justify each answer. So let us see 11a. If the equation ax is equal to 0 has only the trivial solution, then is rho equivalent to the n by n identity matrix. If the equation Ax is equal to 0 has only the trivial solution, that means the columns are linearly independent. So here has only the trivial solution. The columns of A are linearly independent. That means if the columns are linearly independent, according to Theorem 8, we said if the columns of A are linearly independent, which is part E, then A should be invertible. So that means A can be row reduced to the identity matrix. So if the equation Ax is equal to 0 has only the trivial solution, then we have B, A is row equivalent to the identity matrix. So A is invertible, that leads to A is invertible and A can be row reduced to identity matrix. That means if D, then B. So this statement is true. So let us write it here in different color. This one is true. Then for B, if the columns of A span are n, then the columns are linearly independent. This one is true clearly. Here the columns of A span are n. Then we have the columns of A form a linearly independent set. So this one is true. We can say if H, then E also. Then C, if A is an n by n matrix, then the equation Ax is equal to B has at least one solution for each B in Rn. So if the equation has at least one solution for each B in Rn, is this statement true? Here we have the equation has at least one solution for each B in Rn. But this one should be, this matrix A should be an invertible. So this one is false because we need A to be invertible. A has to be invertible. Because we cannot conclude that the equation Ax is equal to B has at least one solution for each B in Rn unless A is invertible or one of these statements is true. Then D, if the equation Ax is equal to 0 has a non-trivial solution, then A has a fewer than n pivot positions. This one is true because if Ax is equal to 0 has a non-trivial solution, that means D is false. The equation has the trivial solution, so this one is false. That means A cannot has an pivot position. So here we can say this one is true. So if Ax is equal to 0 has a non-trivial solution, that means D is false. D is false. So that's lead to A cannot has an pivot position. That means C is false also. So then last one, if A transpose is not invertible, then A is not invertible. This one is true because we had here AT is an invertible matrix. If also A is invertible matrix. Now if A transpose is not an invertible matrix, that means also this one is not invertible. So this one is true. Let's write it in red. This one is true. And we write if AT is not invertible, that means one is false. One is false. This leads to A also is false. So now let us see 12. In 12, if part A, if there is n by n matrix D such that AD is equal I, then there is also an n by n matrix C such that CA is equal I. This is just part J and K. This one is true. If K is true, then J. So this one is true. We can write here if K is true, if K is true, then J also is true. Now for part B, if the columns of A are linearly independent, then the columns of A span Rn. This one is true because here we have the columns of A form a linearly independent set. Then that's mean we have A has n pivot positions. Also, we have the columns of A span Rn. So this one is true. B is true. We can take, so let's say if A is linearly independent set, so that's mean if E is true, then we have the columns of A span Rn. That's mean H is true. Then for C, if the equation Ax is equal to B has at least one solution for each B in Rn, so this one is true, then the solution is unique for each B. Because this one is true also, because we know that the columns of A are linearly independent and the equation has only the trivial solution. So that's mean we have a pivot in each row. That's mean pivot in each row and pivot in each column. That's mean we have only one solution. So this one is true. Now for D, if the linear transformation Ax maps Rn into Rn, then A has n pivot positions. Here this one we cannot say it is true. It say here the linear transformation X to Ax maps Rn onto, and here we have into. This one too is different, so we said this one is false. We can replace the word into by onto. Then part E, if there is a B in Rn such that the equation Ax is equal to B is inconsistent, so that's mean Ax is equal to B has no solution, then the transformation Ax is not 1 to 1. We said for the transformation to be 1 to 1, we have for each B there is at most one X. So either we have one X or there is no X. Now if the system is inconsistent, that does not mean the transformation is not 1 to 1. So this one is false. It should be, we can take off this word not, so it is 1 to In 15, can a square matrix with two identical columns be invertible? Why or why not? This one we say no, because if two columns are identical, that means the columns are linearly dependent, so that means A is not invertibles. So the columns are linearly dependent. That means A cannot be invertible. This is using the theorem. If one statement is false, then the other is so invertible. In 17, so this is 15. In 17, if A is invertible, then the columns of A inverse are linearly independent. Explain why. So in 17, if A is invertible, that means A inverse also invertible. So here, if A is invertible, that means A inverse also is invertible. Since A inverse it is invertible, that means the columns of A inverse should be linearly independent. So the columns of A inverse are linearly independent using the theorem. Independent, right? In 19, if the columns of a 7 by 7 matrix D are linearly independent, what can you say about solutions of dx is equal p and y? So if the columns are linearly independent, we know the invertible matrix theorem is applied for all for the matrix D. So since the columns are linearly independent, that means D should be invertible. That means dx is equal to b has a unique solution. So using the theorem, D is invertible and hence dx is equal to b has a unique solution because it has a pivot in every row. And the columns, because the columns are linearly independent, the matrix will be invertible. That means it has a unique solution. For 20, if n by n matrices E and F have the property that EF is equal I, then E and F compute. Explain why. If EF is equal I, that means both of them is invertible. That means EF is equal FE is equal I. So from here we show that F is compute. So let us write it here. If EF is equal I, because it is here we have EF, it is given here, they equal the identity matrix. That means both of them, both E and F are invertible. That means, so EF, if both of them are invertible, so EF is equal FE. That means, so E and F are commute. Commute, that means we can multiply EF or FE, both of them will give us the same result. Now for 21, if the equation gx is equal y has more than one solution for some y in Rn. So here we have, that means gx has more than one solution, that means we have a non-trivial solution, that means we have a free variable. Can the columns of G span Rn, y or y not? We say G cannot be invertible since it has more than one solution, so the columns of G do not span Rn. So for 21, we can say here G cannot be invertible using the theorem. So the columns of G do not span Rn. Now for 22, if the equation Hx is equal C is inconsistent, that means the system is inconsistent, there is no solution for some C in Rn. What can you say about the equation Hx is equal 0 and y? So if the equation Hx is equal to C is inconsistent, Hx is equal to C inconsistent, that means the statement G, the equation Ax is equal, the statement, yes, Ax is equal to B has at least one solution for each B in R, and this one is false. So we can apply this one here. The statement Hx is equal to C has at least one solution for each C in R and is false. So that means G is false. This leads to D to be false, that the equation of Hx that's lead to, sorry, if G is false, this will give us the statement D also is false. So what is D is false? So Ax, or so, here the D is Ax is equal to 0 has a trivial solution only. So this is the statement D. Now if we apply this one, so Hx is equal to 0 has a non-trivial solution. In theorem we have if the equation Ax is equal to B has at least one solution for each B in Rn, then the equation Ax is equal to 0 has only the trivial solution. Now we have Hx is equal to C is inconsistent. So that means the statement is false. The Hx is equal to 0 cannot has only the trivial solution, it has a non-trivial solution. So we conclude here Hx is equal to 0 has a non-trivial solution. For 23, if n by n matrix K cannot be reduced to In, so that means K is not invertible. What can you say about the columns of K? So for 23, from here, if K cannot be row reduced to the identity matrix, that means K is not invertible using the theorem. So that means the columns of K, the columns of K are linearly dependent, and they do not span Rn, and do not span Rn. This one is linearly. In 28, show that if AB is invertible, so is B. So if AB is invertible, we want to show that B is also invertible. Let us assume let W be the inverse of AB. So that's mean W AB should be equal I, because we assume that the W is the inverse of AB. Now if we take WA as to multiplication of WA, then we multiply the result by B, this will give us also the identity matrix. Now by the inverse matrix theorem, it said if by the J, we have there is an n by n matrix C such that CA is equal I. Also, there is n by n matrix D such that AD is equal I. So by J statement from the invertible matrix theorem, we have here P WA is equal I. So hence, from here, if WA multiplied by B is equal I and B multiplied by W is equal I, B should be invertible. So this thing using the theorem. We said that the matrix is invertible if we multiplied the matrix by its inverse and the inverse by the matrix give us I. From here we assume that W is the inverse of AB. So that's mean if we multiply W by AB, this will give us the identity matrix. Now if we take WA multiplied by B, this will give us I. Now we want to show that there exists B multiplied by WA is equal the identity. So using the theorem, the inverse matrix theorem, this will give us B WA is equal I. From here we see that WA multiplied by B is equal I and B multiplied by WA is equal I. So hence B is invertible. In 30, if A is n by n matrix and the transformation x to AX is 1 to 1, what else can you say about this transformation? Justify your answer. So if the transformation is 1 to 1, that means the statement F is true. This will lead to the I true that the transformation map Rn to R onto Rn. Also, the matrix A is invertible. Since A is invertible, the transformation also will be invertible. So let us write it here. Since A is since the transformation is 1 to 1, since the transformation is 1 to 1, that means the statement which is then F is true. F is true. This will lead to that I should be true also. I true, which is the transformation maps Rn onto Rn. Also, A will be invertible and the transformation will be also invertible. So also A is invertible. This would lead the transformation is invertible. All this information is from the invertible matrix theorem. In 31, suppose A is n by n matrix with the property that the equation Ax is equal B has at least one solution for each B in Rn. Without using theorem 5 or 8, explain why each equation Ax is equal B has in fact exactly one solution. So here, since we said since Ax is equal to B has at least one solution, that's mean A has a pivot in every row. Because it said it has at least one solution, so that's mean A has a pivot in each row. And since A is n by n, and we have a pivot in each row, that's mean also we have a pivot in each column. A has a pivot in each column. Since A has also a pivot in each column, that means there is no free variable. no free variable, only we have the trivial solution. That means AX is equal to B has a unique solution. That's it. In 32, suppose A is n by n matrix with the property that the equation AX is equal to 0 has only the trivial solution. Without using the invertible matrix theorem, explain directly why the equation AX is equal B must have a solution for each B in Rn. If AX is equal to 0 has only the trivial solution, that means A has a pivot in each row. Since A is n by n matrix, that means A also has a pivot in each column. So the A can be reduced to reduced echelon form, and this will give us a pivot in each row and each column. That means the equation AX is equal to B has a solution for each B in Rn. This is using theorem 4 from section 1.4. So let us write it here. AX is equal to 0 has only the trivial solution that means A has a pivot in each row. Since A is n by n, that means A has a pivot in each column. So now if A has a pivot in each column, that means AX is equal to B has a solution for each B in Rn. So this will give us AX is equal to B has a solution for each B in Rn. This is, we can say, using theorem 4 from section 1.4. In exercise 33, T is a linear transformation from R2 into R2. Show that T is invertible and find the formula for T inverse. So Tx1 x2 is equal minus 5x1 plus 9x2, 4x1 minus 7x2. First, let us find what is the standard matrix. We know that Tx is equal Ax. Our standard matrix A is equal the coefficient of x1 minus 5, 4, the coefficient of x2, 9 minus 7. So this is our matrix A. If we can show that A is invertible, then using the invertible matrix theorem, we prove that T is also invertible. So A is equal minus 5, 4, 9 minus 4, it is 2 by 2 matrix. We can find the inverse. Determinant of A is equal minus 5 multiplied minus 7 minus 9 multiplied by 4. This will give us 35 minus 36, which is equal minus 1. So A is invertible. Since A is invertible, that means then T is also invertible. And T inverse will be equal A inverse. So A inverse is equal 1 over the determinant, so that's mean 1 over minus 1, which is minus 1. We need to interchange between these two, so this is minus 7, this is minus 5. We need to put these two with the negative, minus 4, minus 9. So this will give us 7, 4, 9, 5. So now T inverse x1, x2, this will give us the matrix A inverse 7, 495 multiplied by x1 x2, this will give us 7x1 plus 9x2 and 4x1 plus 5x2. So here, sorry, I missed this one. Since A is invertible, then T is also invertible, and the standard matrix of T inverse is A inverse. We cannot say T inverse is equal A inverse. So from here, the standard matrix of T inverse is A inverse. In 37, suppose T and U are linear transformations from Rn to Rn, such that Tux is equal x for all x in Rn. Is it true that Utx is equal x for all x in Rn? Why or why not? So now let us assume that A and B, so let A and B be the standard matrix of T and U respectively. That's mean is, so for U we have T of x is equal A of x. For this one we have U of x is equal B of x. Now we have T and U are linear transformation, both of them, such that Tux is equal x for all x in Rn. So it is given that Tux is equal x for all n. We want to show that, is this one true? Utx is equal also x for all x in Rn, why and why not? So now let us compare. So if we assume that A and B be the standard matrix of Tx is equal Ax and Ux is equal Bx respectively, then so we have AB is equal I, the identity matrix, since A and B are square, they are invertible, and B is equal A inverse. From where we know that both of them are square, because here we have the transformation from Rn to Rn, so both of them is n by n. So now BA is equal I, that means x is ut of x is the identity mapping i.e. also utx also will be equal x for all x in Rn, for all x in Rn. So again, if we have to transformation from Rn to Rn, we assume we have that Tux is equal x. We want to know if Utx also is equal x. If we assume our matrix, we have A and B, both of them will be the standard matrix of T and U, such that Tx is equal Ax, Ux is equal Bx. So now if AB is equal I, since both of them are square matrix, that means they are invertible, and the inverse of B is A inverse and the inverse of A is B inverse. So if we multiply B by A, we get the identity matrix. That means we can write X as UTX is the identity mapping, i.e. also, since this one is the identity mapping, that means UTX is equal to X for all X in Rn. For 38, suppose a linear transformation T from Rn to Rn has the property that Tu is equal Tv for some pair of distinct vectors u and v in Rn. So since here it is given Tu is equal Tv, but, sorry, here we have but, U is not equal to V. So from here we have the information T is not 1 to 1. So for some vectors U and V in Rn, can T map Rn onto Rn? Why or why not? So since we are given that T is not 1 to 1, so that's mean By Theorem 12 in section 1.9, the standard matrix of A of T has a linearly dependent columns. So from here, since T is not 1 to 1, then the standard matrix of T, which is A, has a linearly dependent. So the standard matrix, let us see A, let us write it here. The standard matrix T, the standard matrix A has a linearly dependent columns, has a linearly dependent column. So from here, since we have the linearly dependent columns, that means also we have A is a square matrix because the mapping is from Rn to Rn, then the columns of A do not span Rn. So from here also we can say it also, since A is n by n matrix, so the columns of A do not span Rn. So by Theorem 12, again T cannot map Rn onto Rn, which is the invertible. Also we can say also by Theorem 8 that the invertible matrix theorem, let us see it right here. By Theorem 8, which is the invertible matrix theorem, T cannot map Rn into Rn.